the second part or second topic of part 1, and it's about the overview of electrical power systems. I'm doing this because you guys have a background, mostly probably mechanical discipline biased. So I thought just give you a quick review and maybe a revision about what the basic concepts of electrical power. Now, if you think about electrical vehicles, the center of the electrical vehicle, really the main energy storage device, is a battery. Okay, the battery can be charged externally, like plug-in hybrid vehicles or pure electrical vehicles. It can be charged via IC engine and generator on any hybrid electric vehicles. And of course, it can be recaptured from regenerative braking. And that is really the centerpiece of an electric vehicle, whether it's a storage device that stores energy. But if you think about the main components or main electrical systems on an electrical vehicle, energy storage is only one part of it. There are two other components that you need to consider as well. One is the motor, which is really used to produce the traction effort to drive the motor, traction force or traction output to drive the wheels, but it can also be used to produce electrical energy when you are braking as a motor. And of course, for some of the hybrid electric vehicles, you will need generators, that dedicated generators in addition to the electrical motor, to convert the energy from the internal combustion engines to either drive the motor to either provide electrical power to the motor or to charge the battery. And of course, when the motor, as I said earlier, when the motor is used in the reversed mode, it can also produce electrical power from braking energy as well. So 3 key components here: the generator, the motor, and electrical storage. That's either batteries or ultracapacitors. Now bear in mind that because you're not studying electrical engineering as your main degree, in electrical engineering, motors and generators are very, they are really the same device. Sometimes we call it electrical machines because it's difficult to tell whether this is a motor or it's a generator. Of course, there are particular design issues for electrical motors. If you design the machine to function as a motor, and then there are some optimization issues, so it works best in the motoring mode. If you design an electrical machine to work as a generator, then of course there are particular emphasis on make sure that it works better in the generating mode. But in principle, in any electrical machine can work in both modes. Okay, when it converts electrical power to mechanical power, it is working in the motoring mode. When it works to produce electrical power from mechanical power, then it is working in the generating mode. But for some hybrid electrical vehicles, you will need both. You need motors to drive the wheels, but you need to generate power. You also need a generator to generate electrical power from the engine as well. But for some electric motors, especially the pure electric motors, you need the electric motor itself without the need for the generator. Okay. Now, to make them work, to make the motor, the generator, and to charge and discharge energy from the battery, you need additional devices, what they know as power electronics. Like the diagram I've shown here, if you look at it, you have the generator here, and you have the motor here, you have the battery here. And then all the other blocks here, this rectifier, let me just back. This rectifier, this inverter, this is DC converter, an inverter here, DC to DC converter there. These are all power electronics. Each of these blocks serve a particular function, but broadly speaking, you have these types. Okay? You have an inverter that is normally used to produce a AC current or AC voltage from a DC supplier. Okay, you have a rectifier. Rectifier actually converts alternating, that's AC current or AC voltage, to a DC power source. The converter, on the other hand, is also known as DC-DC converter. It changes the voltage level from one to another. It's possible to get the higher output voltage from a low input voltage, or vice versa. You can generate a lower output voltage from a higher input voltage, but they are both DC, that's direct current. Okay, so 3 different devices. There's a lot of sort of technical details into it, but again, because we are not electrical or electronic engineers, so we're not really can't really get into every single topic of that. But some basics matter. Okay, some general concepts of electrical circuits. And I know you have done some in your, or hopefully have done some in your A levels. So, but some basic circuits or basic laws that matters. For example, Ohm's law. Okay, you will know this. Okay, or you should know this. Voltage equals to current times a resistor or resistance. That is a relationship between voltage, resistance, and current on a resistor device. Okay, so V, remember that equation number 1. V equals to I times R, that's Ohm's law, that's for the voltage, current, and resistance relationship of a resistor. And of course, if you know voltage and the current of a device, then you will also know the power. The power is a product of voltage and current. Okay, V times I give you power. Power is normally measured in the unit of watt, W, or kilowatt, or megawatt. Okay. Now, if you think about the resistor, because V equals to I times R, if I replace the V here in equation 2 with IR, I get I square R. Therefore, for a resistor, if you know the current, you can also work out the power. P equals to I square R. And of course, I can also replace I in equation 2 with V over R. That will give me P equals V square over R. That will also be able, you can use this to calculate the power of a resistor. Okay, so in general, power equals to voltage times current, whether it's a subsystem or it's a particular component. But for resistor, you can use I squared times R or V squared over R. But they are interchangeable. All equations are there. That's power calculation. But for the energy calculation or electrical work, energy or work equals to power times time. Like, the energy, electricity you pay at your house. Okay, you pay them in kilowatt hour. This is a standard unit of energy, so kilowatt per hour. Therefore, the electric work equals to power times T, how long it lasts. The power, if you keep the output at same power level, and longer you do this, the more energy you use. Okay, so power, remember these basic formulas. Okay, V equals to I times R, that's for a resistor. Power in general equals to V times I, that's equation 2. But for a resistor, the power can also be calculated using I squared times R, and P equals to V squared over R. The energy equals to power times time. So we can use that later on to work out the energy stored in a battery or how long it can be used for. Now, based on the simple formulas on the previous page, I'm going to show you, explain this circuit briefly, and I'm sure you have seen this before, or you should have seen this before. So in this case, we have a battery pack. So this long and short bar represent several, or each of them represent one battery cell. So I have 1, 2, 3, 4, 5, 6 batteries connected in series. The total voltage here is E. Okay, so 6 batteries connected in series give me a total voltage equal to E. That's the voltage between this point here and that point here. Now this battery, of course, will have some internal resistances. Ideal batteries don't have internal resistances, but we are not talking about ideal cases. So in practice, you will have some internal resistance. This is represented with this resistor here, R. So that's all inside the battery. Okay, so there's a voltage, there's resistance. Now, any battery will have 2 terminals at output. Now we connect this to supply some kind of a node. So this could be another resistor, for example. Okay, so this is, say this is RL, that's a node. Now if you analyze this circuit, the current going through the battery, going through this internal resistor, and going through the node, they're all the same. So current here is the same as current here and current there. Okay, and the voltage across here equals to the voltage drop across that resistor, which is IR, plus the external voltage as well, that's V. Say the output voltage there is V. Okay, so V plus IR equals to E, or V equals to E minus IR. That's this equation says here. When the current, if you disconnect that load, when there is no node, then this current equals to 0. It does not have current because you open the circuit. When this current is 0, the current going through there is 0. Therefore, I times R equals to 0. Now in this case, V will equal to E. That's why if you take a battery, you just measure the battery using a multimeter, you see a voltage. But if you connect a battery to a circuit, now the voltage between the two terminals of a battery can well be lower because now you have current flowing in the system. Okay. Now also, if you look at that circuit, which I've not written any equations here, is the energy or the power of each part. The power of the battery is E times I when there's no connection. Okay, when I equals not equal to 0. I equals to 0, there's no power output. So E times I is the total power of the battery. Voltage of this, or I square R, is the power lost in the internal resistance. So I square times that R. The voltage output, if you know the resistors here, that will be I square times this resistors. That would be the power of the output node. But because we don't on this diagram, it doesn't show the resistance, but we know the voltage. So if we know the V, we know the I, we can do V times I. That will be the power of the external node. Now power is balanced. The power in this case is supplied from the battery to the power loss here and the power here. So the power of the resistor plus the power of the external node should equal to power of the battery itself. So EI here equals to I square R plus V times I. Okay, they have to be balanced. Okay, these are just fairly basic formulas, and I can use this to, I'm going to use this example to explain a bit more. Okay, for example, a vehicle, say this example says a vehicle is using a 380 watt, 15 kilowatt hour. That's the work or energy stored. Lithium-ion battery pack with the internal resistance 0.4. Internal resistance is this one. This E equals to 360 volts. Okay? The rated current is 330 amps. That means the output, the current in this case, under the rated condition, this I current is 330 amps. Now in this case, I can work out the voltage for each component. I know the current 330. I know the internal resistance. Therefore, if I multiply the two together, I times R, 330 times 0.4, that gives me 132 volts. Then I can use this formula there to work out the output voltage, V. Okay, so the output voltage at the terminal of the battery equals to the total voltage, 380, that's E, okay, or V bat, minus the voltage drop of the internal resistance. Therefore, the output voltage is 248. Now you can see here, the voltage, without the current, the voltage of the battery is 380. But when the current is high, there's another voltage lost inside the battery. So what you see, once you have this kind of level of current, you don't see 380 volts at the output of the battery. You only see 248. But of course, batteries are not always used at the rated current. The rated current means it's really the maximum current you can draw from the battery before you cause damage to the battery. Now, once we know all that, we know the voltage, we know the current. Now we can actually work out the power. So the power of the terminal that's supplied to the external equals to output voltage times current, which will be 81,084,840 watts. But we use a converter, I divide that by 1,000 to give me a kilowatt as the unit. V times I give me a number in watt. V times I is watt, but I'm divided by 1,000, that's kilowatt. The loss equals to the loss of on the internal resistance is 132. That's the voltage drop across the internal resistance times the same current. That'll give me 42.56 kilowatt. Now the total, add the two together, that should equal to the battery power. Okay. Now we know the capacity, the energy capacity, or the energy, the work equals to power times T. Therefore, if you draw the current of 330 out of this battery, we can actually work out how long this battery will last before the energy is completely depleted or is used up. So the total is 15 kilowatt hour. That's EW. EW equal to P times T. Therefore, T equal EW over power total. So 15 divided by total is this power, P terminal, and P loss. So 81 times 81.84 plus 43.56. Work this number out, it's only 0.12 hour or 7.2 minutes. So you can see, although the battery looks reasonable, it's a higher voltage, but because you're drawing too much current out, and then it will only last for 7.2 seconds. Minutes. And of course, I could ask you to work out. In this example, I gave you the output current, but I could tell you how much the external resistance is. Okay, and then let you to work out the current. Current would equal to the overall voltage E divided by the R here plus the node, the R in the node. So total resistance of the two. That will give you the current. In this case, if the node resistance is high, then we're probably not going to draw that much current. Therefore, the battery will last for longer. Now note this number here. Now on electrical vehicles or hybrid electrical vehicles, to drive the motor, the battery tend to have a high voltage output. Okay, at least in the hundreds. Whereas in a normal car, the conventional IC or internal combustion engine car, the battery is only 12 volts. Because we don't need a battery to drive the motors. So there's two issues here. One is the voltage you need to work with the motors for traction, to drive the motors. The other is the lower voltage, typically 12 volts, that you need for other stuff on your car. Okay, like your internal lights, headlights, and electronics and radios, they all work at that range. So on a typical car, electrical car, you will have at least two different level of batteries or volts. One is, let me rephrase. On an electrical vehicle or hybrid electric vehicle, you will need at least two different voltage supply power sources. One is a high volts, hundreds, in the 100 volts. That's typically around 140 volts to 300 volts. That's kind of from typical vehicles on the market. The other one will have a separate voltage as well, which is very low, 12 volts. Now, of course, we don't have to have a second battery for the lower volts. We can use electronic circuit to produce it. Okay, with this, to reduce the high voltage to a lower one supply. But beware, there are two levels of voltage supplies. Okay, so I leave with you another practical question, very similar to what I've done, but I'll separate these into two parts. One is to use the rated current, which is I gave you this. The other one, if I give you the resistance value, that's the second part. Okay, the first part you don't need to know the resistance value because I'm telling you the current. The second one, I'm asking you to work out the current from resistance and work out the input and the voltage drop of the resistor, the output voltage, and power and energy, and how long the battery will last in each of the cases. Okay, it's a fairly simple practice, but it will be very useful for you, for your study. Okay, thank you.